So as we ended the aldol condensation, we talked about another issue. And that issue is, what if our carbonyl is conjugated? In other words, if you think about when we talked about 1,2 additions before for aldehydes and ketones, we also talked about 1,4 additions. What happens if the carbonyl is conjugated? And we said that the key factor always is whether our nucleophile is a good enough leaving group that the 1,2 addition is reversible. And in the case of an enolate, the answer is yes. It is a good enough leaving group that the reaction is reversible. And so the Michael reaction, or the Michael addition, is exactly that. It's a 1,4 addition reaction using an enolate. So mechanistically, it's going to follow the exact same steps we've seen for 1,4 additions previously. The only difference is the nucleophile. And so we can see an example of a 1,4 addition or Michael addition using these two compounds. If we add base, the base will remove our alpha hydrogen and form an enolate. That enolate can then do its 1,4 attack onto the carbonyl. Resulting in a new enolate, and that new enolate can pick up a proton to give us our product. And so if you think back to previous 1,4 additions, the mechanism here, this is the exact same mechanism. We have an extra step because we have to make the enolate, but that's not a new step to us. And then we just have the two steps of a typical 1,4 addition. The nucleophile attacking at the carbon of the alkene, and then the resulting enolate getting protonated to form the product. Now, the example I showed you here was using a ketone as the electrophile. We can use any number of different electrophiles in this reaction, including ketones, as we saw here, aldehydes, esters, amides, and others. But again, nothing new in terms of this mechanism. It's a mechanism we've already seen, we've already learned it, we're just using a different nucleophile. Now, one thing I want to point out is that you may have noticed in this intermediate that we have an enolate present, and we also have a carbonyl present. And so that means now within the same molecule, we potentially have another nucleophile-electrophile pair. And so under the right conditions, we can use that. And in fact, it is used in a reaction known as the Robinson annulation. And for discovery of this reaction, Robinson won the 1947 Nobel Prize in Chemistry. Now, the Robinson annulation is going to look complicated. In terms of its number of steps, it's probably more steps than any other mechanism we've learned or will learn in this course. But probably the biggest saving thing about this reaction is that there's absolutely nothing new mechanistically in this reaction. So you can see we're taking these two relatively simple starting materials, adding base, and in a single reaction, we form this product. So probably looks complicated, seems like there's a lot going on, and we'll see that there is. But it turns out the Robinson annulation is really made up of two reactions that we've already learned. When we go through the mechanism here in a moment, we're going to see that first we get a Michael addition, and then once the Michael addition is complete, we get an aldol condensation. And so that combination of two reactions takes us from these two very, very simple starting materials to a product that has a lot of complexity built in. Now, as I said, the mechanism is complicated. There's a lot going on here. And so probably going to take more than one slide to show this. But let's work our way through it. So the first step, there shouldn't be anything surprising here. We have this dicarbonyl. We know that the alpha protons in dicarbonyls are very, very electrophilic or very acidic. So base comes in, and we remove the hydrogen and form an enolate. And now recall that our second starting material was a conjugated ketone, which we've just learned can be a good electrophile for a Michael reaction. So electrons come down, pi electrons come over to the alkene, and we shift electrons up onto the carbonyl. All right, so that gets us to our next intermediate. We're just going to abbreviate our ester because the ester doesn't really play any specific role in the reaction. So here's where we're going to get the one maybe unusual or surprising step in this reaction. And the reason I say this step might be surprising is in equilibrium, we're going to actually go from a more stable intermediate to a less stable one. And that's something that ordinarily doesn't happen. The reason that that does happen in this case is the more stable enolate, and we say that because it's more substituted, there's nowhere that it can go. If this enolate tried to attack either one of the carbonyls, it would result in a four-membered ring. But if this enolate attacks, we get a much more stable six-membered ring. And so even though it's not favorable for this step to go forward, if this step does occur, then we're able to go on to cyclize. So that first half, that was our aldol. From here, our enolate will initiate our aldol condensation. Our enolate attacks our carbonyl, pi electrons up onto oxygen. Now, the challenging part here is how do we draw this product? Because we know we're getting a ring, but it's not always easy to just envision how that ring forms. And so one of the ways I like to suggest to do that, go ahead and redraw it the way we had it. And then I'm going to erase that double bond because we know that goes away. The negative charge goes away. We reform the carbonyl. We get a new bond forming there. And then the oxygen becomes negatively charged. Now, by itself like that, that's not the most helpful drawing. But now I'm going to number these carbons. And these numbers are just for the purposes of mapping out the compound. And so you can see now we have a 6-membered ring. So I can now redraw that like I would normally draw a 6-membered ring. And then I'm going to number those carbons as well. And then I'm just going to map the substituents. So carbon number 1 has an O minus and a methyl. Carbon 2 has the ester group on it. Carbons 3 and 4 have just hydrogens. Carbon 5 has a carbonyl, and carbon 6 has nothing. But now we've shown the new bond that forms, and we've also converted it into a more understandable structure. So the next step is just that this oxygen gets protonated. And at this point, we are almost done. We just need to account for our E1CB elimination. So we deprotonate at the carbon in between the carbonyl and the OH group. And finally, that O minus can now trigger the loss of the OH to give us our final product. So definitely a long mechanism, definitely a complicated mechanism, but you can see just how quickly we can build up complexity from two relatively simple starting materials. And so let's look at one other example of this. And again, it's going to demonstrate just how useful and just what this reaction can do. So we start with this compound. This is clearly going to be our electrophile for the Michael addition. And this dicarbonyl is going to make for a good nucleophile. So we can deprotonate. And then our enolate will do the 1,4 attack onto our carbonyl. Here's our new bond that forms. And then you recall in our previous example, we had to shift the enolate to the other side, that equilibrium process. We're going to see the exact same thing occur here. So we just get an equilibrium shift over here. Now our enolate do a nucleophilic attack onto one of the ketones. getting us to here. And then once we do our E1CB, we get to our product. And so notice again, we've taken these two very simple starting materials, and we've now got this compound with 3 rings in it. And if you can get this alkene to react with this carbonyl, which is something we haven't learned how to do yet, but certainly something that can be done. And a couple more steps after that. But basically, you know, this Robinson annulation has allowed us to very quickly build up a steroid skeleton. And from the 2 starting materials that we started with here, you can actually get a very, very, relatively easy synthesis of estrone. Again, those 2 simple starting materials, you bring them together, they form the 6-membered ring, and then get the aromatic ring to react with the carbonyl, forms your last 6-membered ring, and then it's just a couple steps to get to the product.